Hi everyone, welcome to my new video in my Mathematics Essential series. In this video, we are going to discuss the graph of y equals the tangent of theta. Okay, you can just Google search what this graph looks like, but what's more important is that you understand why the graph looks the way it does. Okay, if you can understand that, it's going to be easier to understand why the graphs of other trigonometric functions look the way they do. Okay, trigonometric functions, which I have not yet introduced in this video series, but perhaps you are familiar with. So you have the inverse trigonometric functions and you have the reciprocal trigonometric functions. Their graphs will be easier to plot yourself and understand if you can understand the graphs of the three basic trigonometric functions, sine, cos, and tan. And tan is the most complicated of the three. Okay, but let's make it simple and easy to understand. All right, the theme of this video is basically going to be, I'm going to have this set of axes here, all right, a theta y axis, theta for the horizontal axis, y for the vertical axis. And all I'm going to do is just do a bunch of reasoning, collecting information, all right? I'm going to do a bunch of reasoning which tells me, it gives me hints about how the graph of y equals tan of theta must look, okay? It's not going to be very precise, all right? So it's not going to give me the kind of information that a graphing calculator would, as in just tell me exactly how the function looks, all right? But it's going to be, it's going to supply me with a lot of good heuristics for graphing the function by hand, okay? So first, we're not actually going to graph the function, we're just going to plot a bunch of information on this axis, which is going to reveal stuff about the function. Okay, we're going to need a unit circle, because remember, tan of theta, which is what we're plotting, which is what we're graphing, is just equal to sine of theta over the cosine of theta. Okay, and they are defined on the unit circle. Okay, so let's get to it. I'm going to put in some values of theta, so 2 pi, pi, okay, pi on 2, and 3 pi on 2. Okay, now these values for theta being negative, that just corresponds to heading in the clockwise direction measured from the positive x-axis. So that's what it means to have negative angles. Okay, this would be negative pi. Okay, negative 3 pi on 2. Okay, and this would be negative pi on 2. All right. Let's start with intercepts. So let's do theta intercepts first. Theta intercepts, that's what we're finding. In other words, we're looking for places where the graph is going to intersect this axis, if at all, okay? All right, notice that whenever the graph would be intersecting the theta axis, that's when y is equal to 0. So in order to find theta intercepts, you have to assume y is equal to 0, because that's the only value for y for which the graph will be able to intersect the theta axis. So you set y equal to 0. And what does that mean? Well, remember, y is tan of theta. That's the function we're interested in. So this is the same as setting tan of theta equal to 0. But tan of theta is just sine of theta over cosine of theta. So this is the same as just setting sine of theta over cosine of theta equal to 0. Okay, and you can see that in the denominator, we have cosine of theta, and if cosine of theta was to equal 0, this quotient would be undefined, but this quotient just is tan, so tan would be undefined, which means that the only way we can get 0 out of this fraction or this quotient is if the numerator is equal to 0, so if sine of theta is equal to 0. Okay, so the sine of theta over the cosine of theta equal to 0 implies that sine of theta is equal to 0. So now our questions become much simpler. All we have to do now is consider what angles of theta would give us sine of theta equal to 0. And we can head to our trusty unit circle, all right, and we can see that when theta is equal to 0, sine of theta is 0. When theta is equal to pi, okay, sine of theta or sine of pi would be equal to 0. So this corresponds to an angle of 0 and then an angle of pi, okay. So for 0 and pi, I'm going to write some values up here. So for theta, equals 0 and pi, okay, we're going to get sine of theta equal to 0. All right, I'll write a 4 here. All right, but are these the only angles for which sine of theta would equal 0? Well, no, because we could keep heading around the unit circle. Okay, we can get back to where we started, which would be an angle of 2 pi. All right, well, let's include that. But hey, who says we have to stop? We could just keep going. And we would get back eventually to 3 pi. Okay, so I'll put that value in, 3 pi. All right, but I could keep going. And I'd get to 4 pi. Okay, so I'm sure you can see the pattern. Any multiples of pi are going to give you sine of theta equal to 0. Okay, and 0, theta equals 0 here is not a counterexample. You can think of that as a multiple of pi. That's just 0 times pi. Okay, but is it just these positive angles? Well, no. Not only the positive angles will give you sine of theta equal to 0, but you could head in the other direction. Okay, this is just how we interpret negative angles, as being measured clockwise from the positive x-axis. So theta equals 0, theta equals, this would be negative pi, okay? And then you get back to where you started, that would be negative 2 pi. You could keep going, negative 3 pi, okay? Negative 4 pi, negative 5 pi, and so on, okay? So the same thing happens if we're dealing with negative angles, which means I can just say positive or negative pi, positive or negative 2 pi, positive or negative 3 pi, positive or negative 4 pi, and then put a comma here and an ellipse to say and so on. All right, so to express this not as a sequence, actually I don't know why I rubbed that out. Okay, to express this a bit more compactly, okay, what we have are these integer multiples of pi. So 0 times pi, positive or negative 1 times pi, positive or negative 2 times pi, positive or negative 3 times pi, and so on. They're just integer multiples of pi. So any arbitrary integer, let's call it n, okay, for theta equals n pi, where n is in the set of integers, we have sine of theta equals 0, okay? All right. Well, remember, whenever sine of theta equals 0, that gives us tan of theta equal to 0, all right? And whenever tan of theta is equal to 0, that gives us y equal to 0. And whenever y is equal to 0, we know that we have theta intercepts. So those theta intercepts are going to be at these positive and negative, well, just these integer multiples of pi. So what I'm going to do is draw these white dots to say where the graph intercepts the theta axis. So here is an integer multiple of pi. That's 0 times pi, so theta equals 0 times pi. Here, theta equals 1 times pi. Here, theta equals 2 times pi, and you're going to have infinitely many intercepts. Okay. Here, theta equals negative 1 times pi. Here, theta equals negative 2 times pi, and it's going to keep going. So we know that these white dots, which are points that can, to express all of these coordinate points generally, they're all of this form. Okay, they're all of some integer times pi, comma, so that's the theta value, right, comma 0. That's the y value, okay? So that's what all those white dots are. There's some coordinate that has this form here. Some integer, okay, so where n is an integer, okay? Some integer multiple of pi for the theta component and 0 for the y component, okay? So that's some information. Let's see what else we can find out. Well, recall that since tan of theta is defined to be this quotient, sine of theta over cosine of theta, division by 0 is undefined, so cosine of theta cannot equal 0. In other words, if cosine of theta is equal to 0, tan of theta is undefined. So we need to find out all the places where cosine of theta equals 0. And that amounts to determining what values of theta will give us a cosine of theta equal to 0. So what we're doing here is determining to determine where y equals the tangent of theta is undefined. Okay, and where would it be undefined? Well, remember we're after values of theta that make cosine of theta equal to 0. Cosine of theta is equal to 0 there, that's pi on 2. Okay, cosine of theta is equal to 0 there, that's 3 pi on 2. Okay, this whole angle, that whole angle there is 3 pi on 2. Okay, but are these the only angles? Are these the only values for theta that will make cosine of theta equal to 0? No, because just like before when we were talking about sine of theta, we could keep going. Okay, so we'd get to 2 pi, alright? And then we would get to 5 pi on 2, where cosine of 5 pi on 2 would be equal to 0. And we get to 7 pi on 2, 8 pi on 2, which is just 4 pi. Okay, 9 pi on 2, okay. 10 pi on 2, which is 5 pi, and so on. You know, you could just keep going. Every time you arrive at this point, okay, or this point, you're going to have cosine of theta equal to 0. Alright, well, that's pi over 2 and 3 pi over 2. I'll do them in different colors so it's not confusing. And 3 pi over 2, respectively. So that's that angle, pi over 2 radians, or 90 degrees, and this whole angle. Alright, these two, whenever theta is between 0 and 2 pi, alright, so for 0 less than or equal to theta, which is less than or equal to 2 pi, they are the only two. Alright, but notice that you could just keep going beyond 2 pi, keep going around the unit circle. Alright, you're going to keep hitting these points again and again. Alright, you're going to reach them over and over again. So notice that 3 pi on 2 is just a multiple of pi on 2. Okay, it's just pi on 2 times 3. Alright, so when we come back around and we hit 2 pi, and then we get to 5 pi on 2, okay, that's just 5 times pi on 2. Alright, then we continue, alright, eventually we get to here, we get to 7 times pi on 2. So we have these multiples of pi on 2. Alright, I'm going to write down so far what we have. So theta, so for theta equal to pi on 2, okay, 3 pi on 2, okay, 5 pi on 2, and I think I went all the way to 7 pi on 2. Alright, but you can tell that this just keeps going. Okay, we have cosine of theta equal to 0. Alright, so what's the pattern? Well, that's 1 times pi on 2, 3 times pi on 2, 5 times pi on 2, 7 times pi on 2. Okay, it is odd multiples of pi on 2. Okay, but just positive ones? Well, no, because the same thing would happen if we went clockwise from the positive x-axis. Exactly the same thing would occur, just with negative values of theta. So just like before, when we were talking about sine of theta equal to 0, we can say positive or negative values. Okay, so positive and negative pi on 2, positive and negative 3 pi on 2, etc. Values of theta would give us cosine of theta equal to 0. Okay, to express this more generally, we can say, something like for theta equal to n times pi on 2, where n is odd. Okay, and notice as soon as you say it's odd, you're already saying it's an integer. But you should say, is an odd integer or something like that. Where n is, I'm just going to say an odd integer. An odd integer. It's always good to specify what set something belongs to, right? When you're making claims like this. So for theta equal to some odd integer multiple of pi on 2, that's pretty much what all of this is saying. Okay, cosine of theta is equal to 0. Okay, well, why were we concerned with cosine of theta equal to 0? Well, because it's in the denominator of the definition for tan of theta. And whenever cosine of theta would be equal to 0, it would be divided by 0, which would make tan of theta undefined. So we're going to have parts of the graph. So now we're heading back up to put new information in the graph. We're going to have parts of the graph, or we're going to have parts, like regions of the theta y plane, where the graph basically doesn't occupy it because the function is undefined there. Okay, and to indicate that, typically what you do is you put in these things called asymptotes, which are denoted or indicated by these vertical dashed lines. So that's not where 1 would be because that's pi. We're talking about odd integer multiples of pi on 2. So this is 1 times pi on 2, and 1 is an odd integer. Okay. So we would have a vertical asymptote there at 3 times pi on 2. Well, 3 is an odd integer. So we're going to have an asymptote there. And similarly for the negatives. So negative pi on 2, negative 3 pi on 2. Okay. So yeah, it's funny that I drew an asymptote at pi, but also have indicated that we are going to intercept the theta axis at theta equals pi. Anyways, that with Philly. So we have more information that helps us graph the function now. I'm going to move this down because I don't want it to be distracting. And we consider just the function, or just the graph of the function. Now, what we need to do now is understand these asymptotes a little better and know what they mean. Okay, so around asymptotes, you get what's called asymptotic behavior. I'm not going to explain asymptotic behavior too precisely now because it gets into calculus. But basically, if we have, let's say, some function, okay, this is just a quick basic on asymptotic behavior. Okay, let's say we have a function and an asymptote at some value. Okay, some value. Okay, let's say this is an x-axis and this is a y-axis. Okay, and this here is some x value a. So right there equals a. All right. What happens with asymptotes is that, let's say the function is increasing. Okay, let's say we intercept the y-axis and then we intercept the x-axis. What a function does is approach an asymptote, but never actually intercept it. That's it. Okay, let's say the function was let's say it was decreasing. Let's say it goes through the origin. So it intercepts the x and the y-axis at the same point, which is the only point where the x and y-axis cross. Then what it's going to do is it's going to approach the asymptote, and it's going to forever get closer and closer to the asymptote, but never actually cross it, because you understand this asymptote just continues forever. Okay, function is never defined there. Okay, so our function is just going to continue to approach it and get closer and closer and closer, but never actually touch it. It's just going to keep approaching it, but never touch it. Okay, so that's a quick 101 about asymptote. It's not a very precise explanation, but it's good enough for now. Okay, another way to think of how asymptotic behavior works is to say, well, if you consider some point on the graph and some point on the asymptote, and whatever the distance is from that graph to the asymptote, you can always find a smaller one. You see? You can always find some smaller distance, and this continues forever. You can see the distance between these 2 points keeps getting smaller. Okay, and for any distance you find between some point on the curve and the asymptote, you can always find a smaller distance. All right, now this is quite counterintuitive, because if you imagine a lake, all right, and a frog, let's see my attempt to draw a frog. Do I have green? Yes, I have green. Oh gosh, this would be embarrassing. Okay, so here's a frog, and there's his eye, all right, and here's his mouth, all right, and I don't know, here's his feet. Yeah, it's pretty bad. All right, what a frog's bums looks like. I don't know what a frog's butt looks like from memory, but here's my frog. They have more than 2 legs, I guess. All right, I know that much. I don't know about lots of sort of normal life stuff. Okay, I do know math and philosophy. All right, but maybe he has like a little bit of a pointy thing at the end because he used to be a tadpole, so maybe his bum is like pointy shaped. But anyways, here's my frog. Okay, and let's say that this frog is just going to keep hopping towards the lake, all right, and there's some distance between the frog and the lake. Let's say it's like 10 meters, okay. What I've said here about asymptotic behavior kind of can bring to mind some image analogous to a frog that continues to hop towards this lake to take a drink or something like that, or check on its tadpole babies in the lake, but never actually reaches the lake. It seems that so long as the frog keeps hopping towards the lake, it would eventually reach the lake. So that's why asymptotic behavior can kind of seem counterintuitive, but you'll get used to it and you will eventually understand it if you keep pursuing mathematics. Okay, a handy hint from the outset to kind of understand what's going on here is that imagine if we make this rule up for the frog, and the frog obeys our rule, and the rule is that whatever the initial distance is of the frog's hop, so if the frog hops and covers, let's say 2 meters, well, the next hop can only be half the distance that the frog covered. Okay, it doesn't have to be half, it could be some other value, okay, but half makes things simple. So if the frog is able to hop, let's say 1 meter in the first hop, then the next hop is going to be half a meter, okay, and this is going to keep halving. So this will be, 1/4 of a meter, 0.25 meters. That's what that distance would be. This looks like a H, but I'm trying to denote a distance. And you can see, well, once you understand that you can start at 10, halve it, and get 5, and then halve 5 again, and get 2.5, and then halve that again. Okay, you can just keep halving, all right? Then you can get an intuition for why the frog seems to never be able to reach this lake, at least mathematically. Okay, physically, we might tell some story about, look, the frog will get so close, and then it could just stick its tongue out and drink the water or whatever. But mathematically, which is the context we're concerned with, because we're talking about graph of functions and asymptotes, it seems like the frog would never get there, right? Okay. All right. If you're interested in thinking about problems like that, you might want to look up Zeno's paradoxes of motion. So Zeno was an ancient Greek philosopher. Zeno. Okay, so you can look up Zeno's paradoxes of motion. I like philosophical and logical paradoxes and mathematical paradoxes. Maybe I'll make a video series on paradoxes one day. Probably will. That would be fun. So anyways, now that we understand asymptotic behavior, we know what's going to occur near these asymptotes in our graph for y equals tan of x. Just write it up here. Tan of theta, sorry, not tan of x. We don't know where the graph is positive or negative, but we know that it's always going to be heading towards asymptotes and trying to get close to these asymptotes without actually ever intercepting them. Okay, now we just need to consider like where the graph is positive or where it's negative and so on. We need to know when it's above the theta axis and below the theta axis, which is to say when are the y values positive and negative respectively. Well, cast diagram to the rescue. Where's my unit circle? Here it is. Okay. So I'm going to put down a cast diagram, which is just a Cartesian plane where we just write some letters to tell us where the 3 trigonometric functions are positive and therefore where they're negative. So here, okay, in this quadrant, C for cosine is positive, the other 2 are negative. All of them are positive in this quadrant, only sine is positive in this quadrant, and only tangent is positive in this quadrant. All right, let's consider this interval here. All right, so that's between 0 and pi on 2, not including pi on 2. So in interval notation, that interval would be this, theta in the interval from 0 inclusive to pi on 2 non-inclusive. Why can't we include, wrote an inclusive bracket, pi on 2 non-inclusive. Why can't we include pi on 2? Because remember, it's undefined there. We've got asymptotic behavior at theta equals pi on 2. Okay, well, geometrically on the unit circle, that interval is this. I'm going to write a circle here. I'll draw a circle there to say that we're not including pi on 2. Okay, this angle, okay, theta is just anywhere between 0 and pi on 2. Okay, and on the graph, that corresponds to between the y-axis and this asymptote, anywhere above and below the theta axis. Okay, so our cast diagram tells us that we're in this quadrant, and all of the trigonometric functions are positive in that quadrant. So we know that whatever tangent of theta, whatever the graph looks like, okay, it's going to be above the theta axis. It's going to be positive. Okay, now let's consider this interval here. Okay, you know what? I'm going to do these in other colors. You'll see why later, so I can graph it in white. I'll use red and green. Okay, so green for positive, red for negative. Okay, so we can see from our cast diagram and just considering the unit circle that whatever the graph is doing, it's going to be positive between theta equals 0 and pi on 2, which means our graph would emerge from where we said the intercept was, in this case, this intercept at the origin, and it has to exhibit asymptotic behavior because we have asymptotes. So now we know that it must approach this asymptote. So it's going to do something like that. Okay? But what about this interval here? Okay, so from pi on 2 non-inclusive to pi. Okay, it's okay to include pi in the interval because we know that the graph will intersect at pi. At theta equals pi, the graph will intersect the theta axis. Well, that is from here to here. Oops, from here to here. Okay. So we're dealing in this quadrant. Our cast diagram tells us that only sine is positive in that quadrant. So we know that tan of theta must be negative in this quadrant. And I'll shade that in red. Oh, that is not red. It is not the case that that is red. Okay. I'm going to shade this part in red to indicate that whatever our graph is doing, whatever it looks like, we at least know it's below the theta axis. In other words, has negative y values, Okay, so we know that here we're going to have asymptotic behavior, which means that our graph is going to look something like this. Okay, we know that we have to pass through this point. Okay, that's from when we calculated our axes intercepts before, so our theta intercepts. Okay, now if we look at the cast diagram, we can see we end up going into this quadrant. I've got to change colors again. There we go. We end up going into this quadrant. Okay, so that's this quadrant, tan. All right, tan is positive in that quadrant, and that's the interval from pi to 3 pi on 2, which we can see is here, pi to 3 pi on 2. Okay, 3 pi on 2 is not included. All right, so what I can do is I can shade this part of the graph. You know, all this shading is unnecessary. I'm just doing it because I think it might be helpful. Okay, to say that whatever our graph looks like, it's above the theta axis. Okay, now by symmetry, this is just going to keep going. All right, we can talk about the interval from 3 pi on 2 to 2 pi. Okay, you know, 3 pi on 2 isn't included, so I'll draw a circle there to say I'm not including that value. But being in this quadrant of the unit circle and the xy plane, we know that cosine of theta is positive and all the rest is negative. So we know that tan must be negative, which means we know that whatever our graph is doing, whatever it looks like, I mean, it's going to be negative, okay? It's going to have negative y values. In other words, it will be below the theta axis, okay? Now, by symmetry and our interpretation, excuse me, our interpretation of the meaning of negative angles on a unit circle, okay, these negative values for theta, all right, which just happens, which we just encounter when we head to the left from theta equals 0, okay, the same kind of thing is going to happen, okay, because the circle is still symmetrical. It's still the same geometrical object, all right. It's just that we are saying that the angles are negative when we go clockwise from the positive x-axis. Okay, so the same thing's going to happen. Okay, all right. The cast diagram is still going to yield the same information about where all of our trigonometric functions are positive. All right, so rather than really just explain the same thing again, but with negative values of theta, all right, I think you can see that between 0 and negative pi on 2, or between negative pi on 2 and 0, I should say, whatever our graph looks like, it's going to be negative, okay? Negative y values below the theta axis, okay? And you can probably tell now that if we were to carry on this little arts and craft exercise, All right, I'm better at this than I am at drawing frogs, I guess. This is the kind of information you'd get, where green is telling me where the graph is positive and red is telling me where the graph is negative. So maybe we'd have like a little bit of red here. All right, because my graph cuts off here. My theta axis doesn't really extend all that further. Why am I being a perfectionist about the shading? It's not that important. Anyways. Excuse me. We'd have a little bit here too. All right. So all of this information really is just conducive to helping us graph the curve, the function y equals a tan of theta. So let's do it. Let's finish off this part here near the origin. Okay, we know that we would have had asymptotic behavior down here, all right, but then we need to depart from being close to the asymptote in order to hit the intercept that we know our graph must intercept, in this case the origin. Okay, similarly here, okay, we intercept the theta axis at theta equals pi, but then we need to display some asymptotic behavior, so we need to approach this asymptote, but never actually touch it. Okay, and similar thing's going to happen here. All right, but our graph, my theta axis doesn't really extend very far beyond theta equals 2 pi. Okay, I'm going to have asymptotic behavior down here, but then the graph needs to change direction a little bit because it has to eventually meet up with the theta axis. Oh, you see this? I was trying, the pen setting is quite thick, but you see how that arrow was like touching the asymptote? I don't like that. You should endeavor to never have any part of your graph touching the asymptote, right? Especially in an exam, because you really want to display to whoever's marking your problem, if your problem was to graph tan of theta, that you understand what's going on with the asymptotic behavior. You understand that the graph never intercepts these odd integer multiples of 2 pi values for theta. Okay. Now, by symmetry, this kind of thing is going to happen. All right. Maybe if you draw the arrows first, it'll be easier to do the asymptotic behavior without hitting the asymptote. Okay. And now, the asymptote isn't really graphed here. But you see how the graph of tan of theta is just symmetrical? Okay, this symmetry really follows from the unit circle, the fact that a unit circle is symmetrical. Okay, the asymptotes are a consequence of the fact that tan of theta is a quotient, and therefore we'll have values where it's undefined, specifically the values that make the denominator equal to 0. Okay, the intercepts, we found the theta intercepts from setting y equal to 0, and we found the only y intercept from setting theta equal to 0. And now we can get rid of, pains me to do it because I put so much of my heart into it, but the red and green shading, okay, you don't actually have to do any of that shading when you want to graph the function. I was just showing you, or trying to explain how we might collect information about what a graph looks like, okay? And now we have this nice graph for y equals the tan of theta. Okay, I'm pedantic about the fact that some have arrows and some don't. I need to fix this. Let's fix this because we came all this way. All right. Why do things not as well as we could, right? So, oh, the arrow was fine there. Okay. Who's a good tangent curve? You are. Do you talk to your mathematical objects? Let me know in the comments. Bit weird, I guess. All right. So that's the graph for y equals the tangent of theta. I hope this gives you a decent understanding of why the graph looks the way it does. Okay, you could just Google search y equals the tangent of theta and see what the graph looks like. But what's much more beneficial to your mathematical development is that you understand why the graph looks that way. Okay, so if you found this video helpful, please give it a like. Feel free to share it with your friends, and if you would like a notification when I upload a new one, subscribe to my channel. Until next time, bye for now.